Hi. Sound is working. Hi, welcome. We are doing another round of the animation generation collaboration. So let's look at the prompt for this month. It's in the title of the video, of course. So the prompt is Pythagoras Theorem. Create an animation showing a visual proof of Pythagoras Theorem. And for Pythagoras in general, there are hundreds, maybe thousands of different proofs, and especially visual ones. So that will be a lot of fun. Let's see. I think most people will do one or two of the same, but maybe we can get a diverse range of proofs in this month. What I will be doing is the following. For a couple of years, I was working in a project called Toolbox Lehrerbildung, which translates as Toolbox Teacher Training. It's in German. It's an interactive teaching platform for teacher trainees. And if I go over to the tab, we did a lot of Pythagoras proofs there. I didn't code these interactive visualizations myself, but I worked with them a lot. So I want to quickly go through a couple of them to see what's possible, because I don't want to do all of them. So where is the what I would call the standard one? Where is it? Here. This is probably the standard visual Pythagoras proof, but that's not the one I want. Sorry. This is the one I want first, right? That's what I want to show. So this is the general in general the standard Pythagoras proof. You take the right angle triangle, you take 4 copies of them and arrange them with the small squares in this way, and then you can move them about to reveal the big square built over the hypotenuse. And yeah, I find it very satisfying. You can build it with physical materials out of 3D printed blocks or wood blocks. Very, very nice. It's also what I would say a true visual proof, because you don't have to explain anything in the proof itself. Whereas many other so-called visual proofs, you have to explain a lot to understand what's going on. So I really like that. I expect that many people this month will be doing this one. I want to do a proof which only works with the triangle itself. So I will start with, depending on how much time we have, with this one. If we have a right angled triangle, then we can shear the smaller squares appropriately and see that together they overlap the big square, which is very, very nice. So let's do it one more time. We shear them upwards until they meet, then we move them down, and then we shear them again. And this should be very easy to visualize and to program. Hopefully very simple. So this is what I definitely want to do. The very, very big advantage of this interactive version is that if you make the triangle not right angled, you can actually see where the proof fails, because the resulting rectangles you get at the end, they are too large if the point is too wide outside. Hi, welcome to the stream. And if the point is too far inside, you can see that the areas are too small. This is very nice. You can let students explore this proof very interactively. But we want to do this animation in a minute. And what I would love to do, if we have time, we want to do a generalization. You might know that Pythagoras holds true for any shape. If you take any shape and you scale it proportionally to the sides of the right angled triangle, then the 2 small copies together will have the same area as the large area, the area of the large copy. There are different reasons for that. At the end of the day, it always is the reason that if you have a 2D shape and you scale it up by a factor of lambda, let's say, the area gets scaled by lambda squared, so it's always related to squares in some way, and then you can do measure theory, Hausdorff dimensions, whatever you want. You can make it arbitrarily complicated to prove, but it does work. And for n-gons, for polygons, there are a few nice decomposition proofs, and one is this one here. So let's go to the square version. You cut it into this windmill shape, and then you can rearrange everything inside the big square. And maybe if we have time after the shearing proof, I will do this pentagon version at least to make this generalized Pythagoras for pentagons. Let's see if we have time. But first of all, I want to do the shearing proof. And for the shearing proof, I think first of all, we will start by drawing the triangle and the square and everything. And then at the end, I think we only have to calculate the point here at the very top where they intersect. And everything else is just simple movement. So that should be very, very easy, very quick. So let's hop over to code and Cindy.js. So I will do it again in Cindy.js. As always, the code will be in the Git repository in the description when I'm finished. And yeah, let's get going. I already have some colors here in my placeholder file. So let's start by drawing the triangle. I want to do it not responsive, but parameterized, so it's a little bit easier to rearrange. So I want as the general size, I want the radius of this talus circle. Let's make it 10 to start, and then we need 3 points for the triangle. So let's say P is the canvas center, and we go half the radius to the left, and we make 0, and Q is on the other side, so it's probably better to write this as, oh no, one time radius diameter minus radius, and then we go 2 radius to the right at the same height, and then we have PQR. We need some angle, let's say 45 degrees to the left. So N2, what is it? This is P plus radius 0. So this would be the center again, but I want everything in relation to P. So this is the center of the hypotenuse, and then we want to go to the side. Times radius, and what did I say, 45 degrees maybe to the left. And if we draw everything, let's make the triangle directly. So the triangle should be PQR, and we want to draw it as a polygon, so PQR, and then we want to, in the rendering function, we draw the polygon triangle in black. The line size 2 looks nice. I tested that, and something did went wrong, obviously, but that's okay. A plus here. And then we have our triangle. It's probably a little bit too high, a little bit too large, maybe something like that. And now we want to have the squares. So what I think is helpful is to have the vectors which are pointing, like the normal vectors on the sides. And I want to have, I probably won't label it here in our animation directly, but I want this to be the A side, so this is length A, and I want to label or name all the points A, and this is B and this is C, so let's call this the vertical of A, and this should be a 90-degree rotation, so in Cindy.js this is perp, 90-degree rotation of r minus p. And then we get 2 points. The 2 points we want to build here above the side. Let's call them A1 and A2. So this should be R plus word A. And the other one should be P plus word A. And if we now, so this is square A is then P R A1 A2. And if we draw the square A, hi, welcome to the stream. We have our first square. So hopefully I can copy paste it a couple of times. So the B side, this should be, if you make the direction, the orientation the same, Q minus R, Q minus R. And then we have Q and R. And this is B. And this is B. And then we have RQ, B1, B2. And for the hypotenuse, we have P minus Q. And everything with C. The vertical of C, the C corners, and we start with P and then we take Q, the C square, and Q, P, C1, C2, and maybe draw them, not just type them. Right, this looks right. Let's make it a little bit smaller. Oh, much smaller. We want to shear it upwards, right? We want to have this point here. So maybe a radius of 6 looks nice. Yeah, and maybe do some colors. So instead of drawing, we want to fill them. So you can get rid of the size, and let's make that 7% white, 70% white, and then just red, green, and blue, and that looks nice. And it hopefully looks like the preview image on the thumbnail. So the colors, I defined them here at the start. Whenever I am unmotivated and need colors, I'm using just cycles of 80%, 20%, 30%. These are always nice colors. This is the basic setup. And now we want to do what we've seen in the interactive version over in the toolbox. We want to shear the red and the green square upwards so that they meet above the tip here. Then we move them down and then we shear them again. So we need this point here at the top. Let's call it the peak. And the peak, it is, let's say, I want to do 2 lines. I want to take the line extending the top part of one of the squares and the vertical through the point. So this is the meet of 2 joints. So the intersection of 2 connections, and we want to join A1, A2. This is the line at the top of the red square, and we want to join R with a point that goes upwards, so 0, 1. This should be the intersection of those 2 lines. And Cindy.js, if you use the join and meet operations, it will automatically use homogeneous coordinates. We're not doing any fancy projective geometry, so I'm just taking the xy coordinates, and if I draw that, that looks like the peak, and it is also correctly, right, if you go to the interactive version in the toolbox, it is also not only the extension of the square on the left, which we use to calculate it, but also the extension on the right. So again, this is not one of those visual proofs where everything is obvious. You have to make calculations and have to think about that the point in which they meet here, that it is directly over the peak, over the top point, over the R as we called it. But it does work. So this is our peak, so let's get rid of that. Now we want to do movements. Do I want to have, I'm thinking about whether I want to have separate movements or whether I want to make it as one movement, but let's make separate movements. It doesn't really matter. So here in for my animation package, I have the usual setup. I have track data, and the track data always describes the duration of a movement and the pause that comes after it. So the pause is at the moment is set to 0.1 seconds for development purposes. So let's say the first movement we want to do is shearing up. Then we move down, and then we shear down. And at the end, maybe we reverse everything. And so at the moment, everything is 1 second long. That sounds about right. So let's go to calculations. So the first thing we want to do is we want to move the A points to the peak. And in particular, this A1 should end up directly at the peak. So we can, let's say, displacement. The displacement is peak minus A1, and we want to scale that, so we multiply that by T1. T1 is the progress variable of the first movement, so it moves from 0% to 100%, and this is how much we want to displace our square. And now, what am I actually animating? I want to animate a separate copy of our square. So let's say square A movable, maybe that is a good name, probably not, is square A, and then I want to move certain points of our movable square. And let's say I make the movable one in color and the original one as a wireframe. It will stay. Maybe that makes sense. Right, displacement. So this is the displacement, and now we want to say what do I want to do? How do I want to do it? I think I want to write it as the third point, which is A1 at the start. It's probably not very elegant, but let's write it. This is A1 plus displacement. Displacement. And if we do that, this one tip moves over. That's fine. And now we do that same thing with the fourth point. This is A2. So this is the shearing of the first. Again, it's probably not very elegant to make it in that way, but why not? It looks... I think there are some rendering artifacts, but I will ignore them. Right, what we can do is we can make an we can add an easing function, is n out cubic, which gives it a little bit more. Is that nice? In the first video of the series with the sine wave and the circle, I talked about this. For abstract mathematical movements, it's usually nicer to have them in absolute time and not use those easing functions. For something like curves with derivatives, it's very important to do it. Here, it's more taste, but I think without the easing functions, it's probably nicer. Right, so this is the first square. Then we do the same thing for the second one. So now the displacement, so we do everything. So this is square B, movable. Yes, square B. And then we do the same thing, but instead of displacing relative to A1, we take B2, right? So this one here, this is B2, and if we do that and we make again the colored one, the movable one, it's gone, completely gone. Square B movable is square B. Did I movable? Oh, typo. Ah, here, yeah, I could look at the error message, right? Right, now they meet at the tip, at the peak. Fantastic. Now we move them down. So the next displacement, this is the second movement, so T2. And we want to go just straight down. So this is exactly the vertical of C, if I see it correctly. And now we want to do that again, but now we want to do that for every entry. So we say square A movable is, I take all four corners. Wait. Yes, at that point I can do it. I can make it like this. I take all four corners and I say add this new displacement. Right. Equal. Move. Right, the display. First of all, let's. Yeah, it's the same mistake as always. So I have to. I'm a little bit confused why it's not working. So at the start, square A movable, they are at a new position. And then I add the displacement to the new position. So what usually is going wrong here is that I have to define the object within the calculation. So I have to redefine it in every frame. And not outside at the very start, but here, if I copy paste that in, it right. I'm not too sure why I have to do that. after this step. I can't, but yeah, okay. Let's not think about it too much. Oh, what is going on? Right, fantastic. And now we have to shear it down again. And the shearing down now is... Oh, we need a foot point here. What is the foot point? So where is the peak? So we do the same thing again. We take the vertical line here, and then we want the foot point. The foot point is the joint between P and Q. Foot. And now the next displacement. So now we can copy paste it, and now we can make it a little bit easier. So this is and oh. Then it is a little bit more consistent. Right, and now the displacement is we want to move by this amount from the peak R down to the foot point. So this is foot minus R, and this is the third movement. Oh yeah, and we have to do that for the correct corners, obviously. So this is the third one. This is correct, but the fourth one can stay. The second one. That looks good. And correct. So let's lump them together a little bit to make it easier to see. So this is the first movement, the second movement, the third movement. And the displacement is the same, so we can just leave that out and do it for B. And now this is the 1, 2, 3, 4, the first and fourth, so 4 and 1, if I see it correctly. Fantastic. This is the first animation. I think we have time that I can try the second one of the pentagons. That would be quite nice. But this is one way to visually prove Pythagoras theorem. As I said in the beginning, this is one proof where you would very much have to think and reason and argue, mostly that everything aligns properly, that this peak here, that this is exactly above the top point of the triangle, and that it is the continuation of this top line and of this top line, and that everything works out, but at least it is something visual. Right, now we can think about reversing the animation, but that's at the end, that's probably easier to do in an editing software, because I did forget to do it. Let's quickly render it out into a video. With a little bit longer pause. So what we're doing is we're going render mode frames. And now, oh, I hope that works in Chrome. Let's see. Chrome is not very reliable, but now it downloads all frames. Let's see if that worked. No, of course not. Yes, Chrome is very unreliable. So let's take Firefox. Where is it? Let's close it here for a second. And let Firefox do the rendering. So yeah, that's one part that's not super streamlined in my package. That looks right. You only can export the frames individually, and then you would have to use something like FFmpeg. So FFmpeg to turn it into a actual video. Please open. VLC player always takes, please open, a long time now. All right, and I forgot the background again, just like in the first video. But you did see that it does work. No, what do I want? So it does work. I just forgot to include a background. Yeah. What I did for my YouTube channel, I wrote a little Node.js script which does this automatically, download all the frames and then plug them into FFmpeg. But for a few individual videos, you can do it manually. Right, so technically we should have a background, so rendering, fill, polygon, canvas, poly, color, black. Let's see if it works. Whether it works. Oh, right, not frames. Make it real. Right, now this is correct, and then we make it white again. So now the video would have a white background. Fantastic. But again, we still have a little bit of time. I will try to make the pentagon. Let's see how it turns out. But this is the first visual proof. Very nice. So let's just call that version A, and let's make version B now. And I think first of all we get rid of the calculation, and we can get rid of not much else probably. What is going on? Oh yeah. No. Oh, I did edit A. All right. Okay, so that's C A B. Right. Okay, and since we want to do pentagons, we don't need anything here. So we take this setup. So let's try to make a pentagon. So let's call polygon. First of all, how do pentagons work? Pentagons are 72-degree rotations, I think. So we can say A1 is rotate. What is it? It is R minus P, and we want to rotate it by 72 degrees, and we want to attach it to R. And then we 1, 2, 3. We need 3 extra points for a pentagon, I guess. And then we want to rotate it twice and 3 times. And we want to attach that to A1 and to A2. And that polygon A is now P, R, A1, A2, A3. That looks about right. This angle here is a little bit annoying, so let's make it like this. Doesn't really help much. Okay, it doesn't really matter. And now we do our second and third polygon. So B, B, and then we do the same thing. So we do Q minus R, Q minus R. And we have RQ. Let's just double check. Also, we have to attach it to Q. That looks good. And now the last one, C. That's P minus Q. And we attach it to P. And we have QP C. Right. Fantastic. It's way too large now, of course. Maybe something like that. Move it up again. Now I'm wondering if I think the pentagons look correct. So we need a couple of movements. So let's get back a little bit more space. Let's see, it's very tedious work now, but let's see if I can get it done in a reasonable amount of time. So the core insight in this proof is that these small triangles here, which are dark here, they are scaled down versions of the original the gray triangle, the right angled triangle. Again, I won't go into the proof, it's a homework, but that makes it very easy to calculate them. So what do we have to calculate? We have to calculate the center point here, and we have to calculate the halfway points here, and those points then next. So let's do that first. So we need to calculate the center of the green triangle. So this is sum polygon B divided by 5, just the average point. And then we draw. Then we want to have the center points. And I think I want to give them explicit names to make things easier. What are the names we are using? We have B1 to Bx. Do we want to call them x1 to x5? Why not? Will that give me annoying problems? No. So x1 is the center point of, let's go in that way, R Q 0.5. So we need 5 center points. Right. And so we have RQ, Q, B1, B1, B2, B2. Is that another way is to say rotate one of the points 70 to 70. That's probably nicer for everything else we're calculating. Right? Then I don't need to. I think that's nicer. That's nicer. So this is the first point. So this is x1, right? Here. And now we have to move inside. And we have to move inside, so let's call it y. This corresponds, this length here corresponds to this short length here. So this is, let's see whether it works. We have to move from x1 to the center point. And we are moving what's the ratio? So this distance here, half the distance here corresponds to, if I see that correctly, if this triangle here, if these two triangles, let's zoom in. If these two triangles here are similar, and this short one corresponds to this one, this is the hypotenuse, then this edge here corresponds to the edge it already is attached to, so it is a scaling factor of 2. That sounds surprisingly simple, right? So this is right, so we're making it absolute. So we go from x1 to center minus x1 divided by the absolute. So this is the normal vector, which goes off in that direction. And then we scale it by 0.5 times the absolute value of r minus p. That sounds very, very convenient. Right, now this triangle here should be exactly half the gray one. Where is it? Where is the? Let's make. Looks about right. Fantastic. Good. So we define our pieces next. We need names for the small and the large pieces, so I mean there are triangles and quadrangles, so let's call them tris and quads. So tris 1 is r, x1, y1, and now we can say tris 2 is apply tris 1, rotate. We take every corner, we rotate it by 72 degrees around the center. And if we now go here, so I want to have a similar effect where it is gray or dark and light. So let's say we have fill poly tris 1. Let's make it a little bit darker. Right. So this is now this triangle. Oh, I can go much further. Right, and now why is this? Oh, right. I have to. And that looks, if we compare it, that looks correct. If we go to a 120-degree triangle, perfect. Right, so we don't, that's much nicer. We don't define everything. So we have, and this is, isn't it nice when you can copy paste all of your stuff? Fantastic. Now these are the small bits, and now we want to have large bits, which we are calling quads, because you have quadrangles. And the first quad is probably this one here. This one here, right? Or is it this one? I think it's this one. That makes more sense. Let's see how it moves. So the first triangle just moves down and it ends up here. Yeah, let's make that one the first. So this is if we start with R, we go to y1, then we go to the center, and then we go to right, so this is of our last triangle the x point, which is the second one. And if I did everything correctly, we can get some nice quads. And instead of lerping to black, we lerp to white. Yes, fantastic. It didn't work. So let's get. Okay. Quad is, I take R. Where is R? R is this one here. Then I take Y1. This is still correct. Then I take the center. Oh, I have to. Again, I should look at the error message. I'm not used to it being at the bottom. I always have it on the right hand side. Right. This looks nice. Let's make it a little bit less intense. Maybe something like that. Let me make it more. It's okay. And now the rest should fall in line. Oh yeah, of course I have to rotate the quad and not the tris. Fantastic. We have some rendering artifacts here where the polygons meet, but that's okay. After all, we want to move them, right? So let's get moving. So we want to fade in the small bits, then move the triangles, move the quadrangles, and move the red polygon. So these are the movements we want to do. So fade in the bit. So again, we have to think about what is static and what is moving. these things are all moving and we want to actually move them. Do we... So what I'm thinking now is, do I want to, as we did with the shearing, do I want to calculate how I have to move them individually? Because the triangles, if we look at that, the triangles move at a different... I mean, it's relatively easy to calculate where they are going. So what I'm thinking is, do I want to calculate the displacement as before, or do I want to calculate the final position of the whole triangle and then just say, please move there? And let's see how those chunks move. They have to rotate by, I assume, the same degree. And then they are also moving. So the corner, so the corner of the quad, which aligns with the corner of the pentagon, so this one and this one, they all end up at corners of pentagons again. So I think it's probably fairly easy to calculate the displacement and movement for every individual piece. Let's try to do that. So first of all, we take our pieces and we redefine them in calculation again so that we can manipulate them more easily. And the first movement is the movement, well, the first movement is fading them in. So we say, so they fade in. Maybe it is advantageous to have the lines here. Let's maybe do that at the end. Do I want to do that now? I don't like to do that this way because the problem now is that the lines here, they are overlapping. There are several lines rendered on top of each other, which technically, because of rendering reasons, makes the edges, the lines, a little bit wider. They start to bleed a little bit out into the background, into the environment, if you render lines, copies of the same line on top of each other. But I think I don't care. So now with lines we can make that a little bit more subtle, but that's okay. And now we want to move them. So let's see where the first quad, the first triangle is going. The first triangle is going displacement. The first triangle is moving from R to P. So this is P minus R T1, and then the whole triangle is moving. So tris 1 is, yes, tris 1 is the whole thing, displacement. And of course we want to have movement too. What is going on? Tris 1. Right. Appear and move. Let's keep the speed. Right. And now we repeat that. Very tedious. I told you it's not too much fun, but hopefully it will be done quicker. So let's zoom out a little bit. The second triangle, it moves from it moves to B1, right? It moves to B1 and it starts at Q. And the next one, it goes from, oh, C1, of course. I should label things. From B1 to 2. So this is C2, B1. There is a systematic permutation, but because I didn't label the points from 1 to 5, I have P, Q, and R in it. It's a little bit weird. So this is going from B2 to C3. That makes sense. And the last one moves from B3 to Q. Fantastic. They are now, what I'm now thinking is that they are overlapping each other. So we have to, let's make a cheeky little hack. If T2, this is the movement we had. If this is smaller than 1. So while this movement is moving, we render them in this order. This is very, very bad hack, but it probably works. And else we do it in the opposite order, because now we want to move the quads, and when we move the quads, we want to see the quads, right? Oh yeah, the movement of the quads. We still have to move them. So the first part is more or less the same. We just have to figure out where everything is going. So instead of the triangles, we move the quads, and instead of movement 2, we make it movement 3. And now we have to find out where everything is going. So let's see. The first quadrangle, which is this one, it goes from R to Q. So based probably just the other way around. So I hope this is exactly this list of points here at the start, just the other direction. That sounds right. So from here to here. The second one, which is this one, in our notation, it moves in the other direction, right? It moves to P. Oh no, it's the same. It's the same, but cycled, right? So P. The third one, this is this one. It goes from B1. That's correct, to C1. Right. And if we look at that, fantastic. We still have to rotate them, of course. And it's probably best if we pretend that these are actually pieces we are moving, to move them. Oh, right. This has to come along. First of all. Very, very bad copy pasting, but I don't care, I think. So it would be much better to store them in separate lists and then say, please draw all the lists. But yeah. So that probably looks better. And of course we want to have most of the things behind it. We want to have the last polygon at the top. Maybe this will somehow... Right, that looks good. And now we have to rotate those things. And if I see it correctly, we have to rotate this quadrangle 180 degrees, I think. So here we also say rotate by 180 degrees. And we want to rotate around the corner point. The corner point should be the very first one in every quad. Oh, and oh, what is going on? So first of all, we have to use the quad. Again, it would make much more sense to store them in a list and to operate on the list. But okay, and of course, this will now just have rotated everything, so we want to rotate incrementally. We lost one. We lost one. Right, that looks very much like the animation from the toolbox. We still have a little bit of that they move below the red pentagon, but I would ignore that now. Fantastic. And now we have to move the red pentagon as the last movement. So we have to find a new displacement. So let's define it as final displacement. We only need to calculate it once. It's not super dynamic. This final displacement, I mean, what do I want to move? Do I want to move so first of all, I think I will fade that out. Alpha 1 minus T1, then it is gone. Oh, what is going on? Oh, right. So this is, let's make it if T1 reached the end, make it 0 otherwise. So it just will disappear at the end and then it is gone. That makes more sense. And here again we want to move the polygon, so let's have, where's the definition? The definition is here, so we have polygon A movable is polygon A, probably even wrong, right? Movable, whatever. And then we fill in the movable one exactly the same as before. And this is the rendering, and now we do this. So this is the last displacement. This is the sum of polygon C divided by 5 minus sum of A, polygon A divided by 5. And this is the last movement, so that's T4. And then we move our pentagon. So movable polygon A, movable. Not very interesting animation here at this point, I'm aware, but that's okay. So now the last polygon should move into place, but we still need to rotate it by 36 degrees, I guess. So this is rotate. So this is the center around which we rotate. So rotate the thing is 36 degrees times T4, so over time of our fourth movement, around the center again. Fantastic. Now it looks a little bit weird because it doesn't have its own border, so just double the border. Yeah, and now you see here you can see the rendering issue with the overlapping lines. It's not ideal, but I think for now it's okay. And as a final test, let's try it with a few other triangles. So it doesn't work if you move the tip, so you can see it in the toolbox. If you move the tip, where's the decomposition? This is the decomposition. If you move the tip too far to the right, it won't work anymore because the decomposition will overlap here in the center. So if you have an interactive version, you will have to find out where this point is and stop, where the angle is, and stop the point. So if you zoom out for triangles, it's quite early, and the higher the vertex count, the further to the right you can move this, but at some point you have to stop. And I think for polygons, for pentagons, it's at least safe to go over the 90-degree border. So let's say 90-degree. And 170-degree. Fantastic. Right, and if you are into coding and want to work with that, try to do all the calculations here that it works for an n-gon. So this is the original we had, and yeah, that's the second visual Pythagoras proof, and it's not even for squares, it's for pentagons. I won't bother rendering it out. I'll just stop here after, well, I think we did work on the animation itself for about an hour. Talked a little bit about the interactive stuff beforehand. And yeah, these are the two, so this is the second one, these are the two versions of visual Pythagoras proofs that I would like to provide this month. So you have shearing, and we have this decomposition proof. I think it goes back to Henry Perigal, at least for squares. This is probably a generalization. I don't know if he himself did this. But yeah, visual Pythagoras. I hope you enjoyed it, and I will see you next month for the next prompt at the latest. Goodbye.